This is lesson 1, areas and distances, right hand, left hand, and midpoint, Riemann's sum, and distance. This can be found in chapter 5.1 in your book.
So we can talk if it's the increasing or a decreasing function. So if it's an increasing function, the right hand sum will be an overestimate, while the left hand sum will be an underestimate. If it's a decreasing function, the right hand sum will be an underestimate, and the left hand sum will be an overestimate. Some quick notation, f of x will be, so it's the height of the rectangle. We have delta x will be the width of the rectangle, and we have delta x is equal to b minus a over n. So b is the right side of the interval, whereas a is the left side of the interval, and n is the number of rectangles. Now I'll talk about limits for just a few seconds. So it's the limit as n approaches infinity. It'll be the sum of all of the function and the height of the rectangle and the width of the rectangle is equal to the integral as from b to a, or a to b, as the function of x. And so here you can see that we have this written out. So we have the right hand sum and the left hand sum. So it's the sum of the function of x plus 1 delta x plus x sub 2 delta x, and so forth, so on. So to put right hand and left hand sums into action, here's an example. So you're giving time and velocity in feet per second, times in seconds. So to cancel out the seconds, you just, as I did here, you do seconds times feet over feet per second, and then the seconds cancel out and you're left with feet. So this table, for a left hand sum, you're going to go from 0 to 12, 12 to 24, 24 to 36, and 36 to 48. The intervals in there are from 0 to 12, 12 to 24, 24 to 36, and 36 to 48, which are 12. So when you come over here, you're going to do, you can see that also with this equation, delta x is equal to b minus a over n. 60 minus 0 divided by 5 is 12. So what you're going to do in plugging the numbers in, you're looking for 5 points. So it's the interval times the first point on the table. So it's 30. Then you're going to add that to the next one, which is 12 times 28 plus 12 times 25 plus 12 times 22, and then last the 12 times 24, and you're going to make sure you leave out the 27 because that is not part of the left-hand sum. To simplify, you could also just do 12 times 30 plus 28 plus 25 plus 22 plus 24. You are left with 1548 feet. And for the right-hand sum, I have that written incorrectly, but it's the right-hand sum. You're going to do the right hand most points on the table, so 27, 24, 22, 25, and 28. So here you have 12 times 28 plus 12 times 25 plus 12 times 22, 24, and 27. You could also do 12 times that entire parentheses added, and then you're left with 12 feet. So to know if this is an overestimate or underestimate, look strictly at the table for a second. Is this an increasing or decreasing function? That's how you can ask whether or not it's an over or underestimate. And unfortunately with this table, you're not able to see because you can't tell because the function is not strictly increasing or decreasing. Next, when it comes to Riemann sums, we're going to talk about midpoint estimate. Midpoint estimate gives the most accurate estimate because it is between the left hand sum and the right hand sum estimates. So here, just given an equation and plugging it into the formula, you have x squared plus 1, where a is negative 1, b is 2, and I found n because I plugged it in. Delta x is equal to b minus a over n, which is equal to 2 plus 1 over 6, which is 3 over 6, and simplifies to 1/2. So the midpoint formula is the delta x times the midpoint of x sub 1 plus the midpoint of x sub 2 plus the midpoint of x sub 3 plus so forth and so on. Now looking at a problem you can use for a midpoint, it's the integral from 0 to 3 and the equation 8 divided by 1 plus t squared plus t cubed. and we're looking for m sub 6. So of course you're going to be doing delta x times x plus 1 plus x sub 2 plus x sub 3, so forth to x sub 6. So what you're going to do is you're going to plug in values to find the midpoint. You can see I did that here with this table. So I did 0, 2.5, 5, 0.75, 1, 1.25, 1.5, all the way up to 3, increasing by 0.25 each time. I took those values, plugged it into the equation 8 divided by this 1 plus t squared plus t cubed, and I found these values. It asked for 6, so you can see what I did here. I found the midpoint of each point. So I did 0 to 0.5, 0.5 to 1, 1 to 1.5, and so on. This gives me an interval of 0.5 or 1/2. From there you can see the markings I did on the side just to show what the midpoint value was. And as you come over here to this equation where I plug numbers in, I have 1/2 times that 7.42 plus 4.3, 0.03, and so forth, so on. It gives me a value of 7.40. I plug that into Calc tool, and it gives me a rough estimate of 7.39. Calc tool is not an efficient value answer, but it's a way to check your answer, and I know this answer is correct. One last thing is that this table is a consistently decreasing function, which means if you were to take the right hand and or left hand sum, the right hand sum would be an underestimate, while the left hand sum would be an overestimate. You can now see why midpoint, based on this table and this equation, is a more accurate estimate.
My name is Robin Sarah Dyson, and I will be doing an example in the book, number 5 in chapter 5.1. So the question is, estimate the area under the graph of f of x, 1 plus x squared, from x negative 1 to x2, using 3 rectangles, using right endpoints, and then 6 rectangles. B is using the same A with left endpoints, and C is using A with midpoints, and then D we're going to discuss which method was the best estimate. So this is part A of number 5. On the right we have 3 rectangles of the right hand estimate, and as you can see, 3 estimates isn't too much, and it gives us a total of 8. Using this method you can usually count the boxes if it's a small number of rectangles you're using, and we just use the formula R3 equals delta x, and then with the delta x you plug that into the equation. So if you have 1, then it would be 1 squared plus 1, which equals 2. And the delta x, as you can see, is 1. It's the width of the rectangle, which you multiply times the height to give you the area of that rectangle. On the left, it becomes more accurate with 6 rectangles. You can see that the number goes down, and in order to get more accurate estimates, you might want to make a table, plugging in numbers to your original equation to find the exact value. So right-hand estimate, you can see that most of the triangles go over on the rectangle. There's some edges that are over, which means that it's going to be an overestimate of the function overall. And this gives us our right estimate. Here we have part B, which is the left-hand estimate. On the left we have 3 rectangles, which again is a small number because the rectangles are under the equation, which means that it's going to be a smaller estimate. Again, you can pretty much count the rectangles, count the blocks, and that gives you the area. For 6 rectangles, you have more accurate of an estimate, and by this you need to make another table and plug in exact values. Make sure that with the equation you're not estimating where the points are, you actually plug the numbers in to get the exact y value to plug into your equation. This is the left-hand estimate, which is an underestimate. This is part C of question 5. This is the midpoint estimate, and using Riemann's sum, again 3 rectangles, we see that our delta x is 1, so delta x times each value. So for negative 0.5 you have 1.25, for 0.5 you have 1.25, and for 1.5 you have 3.25. By using this equation, this gives you the midpoint estimate. 6 rectangles gives you more accurate of an estimate, and this is where it gets more tricky because you need to have smaller values for your delta x, and you need to plug that into your equation to get exact values again. So by using this method, the midpoint Riemann sum, you get more accurate of an estimate, and It may be harder to find exact values if you're not giving the equation, but make sure that you plug it in to get accurate estimates. This is part D of question 5. The question was from your sketches in parts A through C, which appears to be the best estimate. And here you can see that the midpoint gives the most accurate estimate because of it's between the lower, which is the left Riemann sum, and the upper, which is the right Riemann sum. So M6 would be the best because the claim would be the more rectangles you have, the better estimate you're going to get, because the more rectangles you have, the closer to infinity you get, which infinity leads into limits and leads into our integral. So you want to have more rectangles as much as you can. And here on the bottom you can see that L3 gives the least estimate, whereas R3 gives the most, and M6, midpoint 6, would give you the best estimate.
My name's Donald Hyatt, and this is continuation of areas and distances, and this is distance. So distance is velocity times time, and in these examples it is pretty much the exact same as Riemann sums. Here you see the left-hand sum where it's the first term, and then the second to last term, as you see, is t of n-1, and then you see the right-hand sum, and that's to find the total distance traveled from t equals a to t equals b. And as you saw in the other examples, delta x was the width, and in this delta t is the time, but they're the same exact things. And when looking at an overall equation like this, the f of t of 0, delta t is the distance traveled at interval t equals 0, so any number you place there would that be the interval. And the left-hand sums, right-hand sums would be how you would find the total distance traveled from the bounds that are set by the problem.
So this has been lesson 1, areas and distances in Riemann sum. Thank you for watching, and have a great day.